Hello, everybody. Today I will talk about polynomials, polynomial ring. So let R be a ring. Let's give some intuitive idea. A polynomial in one variable with coefficients in x in R is an expression of the form f of x is equal to a0 plus a1 plus ax plus a2 x squared, blah, blah, an x to the n, where ai's are from the ring R, and an is not 0, and x is a variable. Variable, whatever that means, variable that may be assigned an element of R. So here is more precise definition. We will give a more precise definition of this. So here is, let's define. So let there be a ring. Later it will be a commutative ring with identity, usually. Suppose for now, let R be a ring and let Rx denote the set of, let's say, elements are AI, or we may define it like that. It is the sequence A0, A1, A2, etc., such that these AIs are integer from the ring R, and almost all of these AIs are 0. That means only finitely many AIs might be non-zero, and all the rest are 0. Namely, there is an n such that a k is equal to 0 for n is greater than k. That's a precise definition. Namely, this is from the, just like from the calculus, these are sequences in R, which are eventually 0. Eventually 0. So that means after a certain place, all the terms are 0. So if you take two elements, A, B from R, let's define addition and multiplication. Addition is A plus B, just defined to be AI plus BI. Namely, it is just A0 plus B0, A1 plus B1, etc. Like that. But A times B is defined rather differently. Namely, let's take A0, A1, A2. This is A. And let's say B is B0, B1, B0, B1, B2. We define it like that. So we define first term is A0 times B0. Second term is A0 times B1 plus A1 times B0. Namely, we take the product of all elements whose indices are 0. The sum of their indices are 0 in the first coordinate. Some of the indices are 1 in the second coordinate. And in the third coordinate, it is A0, B2. And some of the indices are 2 in this case. A1, B1, plus A2, B0, etc. So we may define it like this. This is CI, where CI is CI is the sum of the elements from J is from 0 to I, a J B I minus J, product of these elements. So here is a theorem. If R is a ring, then this Rx is also a ring with the multiplication defined above. If R is commutative, which will usually we will have that. If R is commutative, then Rx is commutative. And if R has 1, then Rx has 1. Namely, the identity of Rx is you can take it. You can check this. So if you multiply any A from the left or right hand side of by 1, you get 1. Okay. So the proof of this statement is just a matter of checking these properties. So consider this addition and the multiplication. So I will leave this as an exercise to you with the proof. It is very elementary. It's elementary. And left as an exercise. Okay. So now, let me give one example. So, and the 0 of this Rx is 0 of Rx is that all elements are 0, or the entries are 0. Remember, 1 was 1, 0, 0, etc. Okay. Now, so let's define a function like this, phi from R into Rx by R. Phi takes element of an element A of R to A0, 0, 0. So it's easy to check that this phi is a ring homomorphism. And it is 1-to-1. Namely, it is a monomorphism, so that we can see, so that we can identify R with its image in Rx by the above phi, so that R becomes a subring of Rx. So now suppose, from now on, suppose that R is a ring with identity. R has 1. Then if R has 1, then yeah, as we the above, the identity of 1 is here. We assume that R has 1, so that R is 1 0 0 0. Let's denote 0 1 0 0 by x, and let's take x times x times x, which is 0 1 0 etc. times 0 1 0, and if you check that, this is 0 0 1 0 0. Oops, 0 0. This. And in general, this is we denote by x squared. In general, x to the n is x to the n is 0 0 0 1, and then after 0 0 again. So here there are n zeros. So this is the n plus first entry. Okay. So we set also, for convenience, just like in the integer case, we set x to the 0 to be 1, namely 1 0 0 etc. Okay, then if we have if a is a0, a1, a2, etc., then we can write this as up to, let's say, an, and then the rest is 0, I suppose. The rest is 0, so we can write this as a0 times 0, the rest is 0, plus 0 a1 0 0, plus next is 0 0 a2 0, the rest is 0, and plus 0 0 an 0, etc. So since the addition is component wise, it is like that. So we can write this as, this is, the first component is a0 times 1 0 0 0, which is 1, plus a1 times 0 1 0 0 0, so it is x, and a2 times x squared. This was, remember, this is a2 times 0 0 1, and the rest is 0, etc. So that when you have 1 here, it's x squared, etc., and an times x to the n. Or we just simply write this as a0 plus a1x plus a2x squared plus an x to the n. 1 times a0 is 1. Since we see R as a subring of Rx. So with this convention, with these conventions, if a is a0 plus a1x plus a2x squared plus an x to the n, where an is not 0. Usually we take the last entry to be non-zero, and b is b0 plus b1x plus b2x squared plus bm x to the m, where bm is not 0. Then a times b becomes the product of these two polynomials becomes then A times B becomes A0 first component A0 B0 plus A0 B1 plus A1 B0 times X plus A0 B2 plus, you just multiply the component by, so that you multiply these coefficients so that the sum of the indices are 2. A1 B1 plus A2 B0 X squared, etc. And then at the end we have AN. The last term is AN BM times X to the N plus M. Okay, the last entry, of course, if R has 0 divisors, this AN times BM might be 0. So this X is called an indeterminate. Okay, so here is the definition. Definition of that probably you know from the real number, from the polynomials, from the real numbers, on real numbers. Okay, here's the definition. So let f of x be this polynomial, a0 plus a1 x plus an x to the n, where an is not 0. Then we say that the degree of f is this highest power, which is n. This is the degree of f. And we write the degree of a f of x, or f of x is n. This the coefficient of the highest power of the term which has highest power is called the leading coefficient. This an is called the leading coefficient. So, for example, if we have, let's take ring to be, for example, this Z4 or Z. If you take f of x to be, let's say 1 plus x plus 2x squared plus x to the 5, for example, degree of f of x is 5, and the leading coefficient is the coefficient of x to the 5, which is 1 in this case. Okay. And if we continue with this definition, if the leading coefficient is 1, as in this example above, leading coefficient of f of x is 1, then we say that f of x is a monic polynomial. Is monic. Monic means the leading coefficient is 1. So, for example, let me give one example. So the 0 polynomial is just 0. 0 polynomial. So if all the coefficients are 0, 0 polynomial is denoted by 0, as we showed. We also denoted above, denoted by 0. So namely 0 is 0, 0, 0, 0, etc. or 0, 0 plus 0 times x plus 0 times x squared, etc. And by the definition, so in the definition above, when we define the degree of f, we assume that the leading coefficient is not 0, so that f is a non-zero polynomial. When f is a 0 polynomial, if so, by definition, the degree of the 0 polynomial is minus infinity. It is convenient to define as minus infinity, and note that the degree of f is 0 if and f of x is 0, if and only if f of x is constant, and where this constant is not 0. So that agrees with the definition we gave above. So here's a proposition. Here's a proposition. Suppose that R is a ring with 1. So we will always assume that R has 1. So let R is a ring with 1, and f of x, g of x, f of x and g of x are two polynomials over x over R. Then the degree of f of x plus g of x can be at most the degree of the highest of them. So it is not equal, but it's less than if it's at most the degree of f of x and the degree of g of x. It might be smaller, but not greater than these. And the second, the degree of f of x times g of x is less than or equal to the degree of f of x plus the degree of g of x. So it may not be equal, and the equality with the equality in this, let's say this is A, B, equality in B with equality in B if R has no zero divisors. So if R has zero divisors, the degree of f times g might be smaller. I will give an example of this. So let me just prove A, and I will leave the proof of B to you. So suppose f of x is a0 plus a1x plus an x to the n, and f of g of x is b0 plus b1x plus bm x to the m, and we may assume that n is less than or equal to, we may assume n is less than or equal to m without loss of generality. So that f plus g, so that f plus g, f of x plus g of x becomes, the first term becomes a0 plus b0, second term is a1 plus b1x, blah, blah, an plus bn x to the n, and then Bmn plus 1. If m is greater than n, it is n plus 1. Bn plus 1 x to the n plus 1, etc. Bm x to the n. So that the degree of so that this Bm is not 0. With Bm is not 0. If f of x or g of x is 0, it's clear. So assume that they are not 0. Assume that they are not 0. If Bm, so that the degree of f of x plus g of x is less than, it might be less than m, less than m. This is the degree of less than m. That is the maximum of the degree of f of x and the degree of g of x. Okay, and I will leave this B as an exercise to you. So this was A. This is exercise, elementary exercise. So in the case, so if you look at this example, so let's take R to be Z4, for example, namely Z modulo 4. So f of x is, let f of x to be 1 plus 2x, and g of x to be, again, 1 plus 2x, for example. Then f of x plus g of x becomes is just 2, because 2x plus 2x is 4x, which is 0. So that the degree of f of x plus g of x is less than 1, which is the maximum of, which is the degree of f and degree of g. Also, if you look at the product, that is, so the degree of here, degree of f of x is 1, degree of g of x is also 1. And let's look at the multiplication. This multiplication becomes 1 plus 4x. 4x is 0, and so let me do one by one. It is 1 plus 2x, and that is 1 plus 2x plus 2x plus 4x squared. But in R, 4 is equal to 0. In Z4, 4 is equal to 0. So the result is 1. So that degree of f of x times g of x in this case is 0, although the degree of f is 1 and the degree of g is 1. So it is less than the degree of f plus the degree of g. Okay, but okay. So here's a corollary of the statement. If R has no zero divisors, then f of x is, so if R has no zero divisors, then we have this degree of f times g is the degree of f plus degree of g by the above proposition. So here we say that then this R of x is a unit if and only if f of x is equal to R is a constant, f is a constant. non-zero constant, and are not zero, but it's also unit in R. The reason is that, so we assume that R has identity, of course. R has 1 here. Okay, here's the proof. If this way, if R is unit, suppose f of x is unit, this implies that there is a polynomial g of x such that f of x times g of x is 1, but no zero divisors. R has no zero divisors. This implies that, so degree of 1 is 0, degree of 1 is 0, which is the degree of f times f of x times g of x. But since R has no zero divisors, this is the degree of f of x plus the degree of g of x. So this implies that, so we don't need these parentheses, here we do. This implies that since the degree of f of is not a zero polynomial, because it's a unit, and so that the degree of f of x is 0, degree of g of x is 0, so that f of x is some constant r, and g of x is also some constant, another constant. So they are constants, constant polynomials, and the 1 is equal to r times s, and r is so that r is a unit in R, the ring R. And conversely, if R is a constant polynomial, which is unit, then f of x is unit. That converse is clear, very clear. And here's another corollary. R is an integral domain. Integral domain. Remember what's an integral domain? Integral domain is a ring, commutative ring with 1, which has no zero divisors. So think of integers. R is an integral domain if and only if Rx is an integral domain. Okay, this way, proof of the corollary. This way is, since this is, if R is an integral domain, then R of x is an integral domain. So let's do it this way first. Conversely, if R is an integral, R is a subset of R of x. So R has no zero divisors, since Rx has no zero divisors, so that R has no zero divisors. So Rx has, so if Rx is commutative ring with identity, then R is a commutative ring with identity. And since Rx has no zero divisors, that means since R is a subset of Rx, this has no zero divisors. So that R is an integral domain. Conversely, this way, this way. If R is an integral domain, then R is commutative ring with 1. Commutative ring with 1 implies that R of X is commutative ring with 1. As we stated above, and that's clear also. And only we need to show that R of X has no zero divisors. We need to show R of X has no zero divisors. So let f of X is a0 plus an x to the n. So there must be, let me write second term as well, a1x plus, here there must be 3 dots, not more, not 4, not 2, an x to the n. Suppose that this is not 0, and the g of x is not 0. b0 plus b1x plus bm x to the m. Suppose that this is not 0, so that an is not 0, bm is not 0. We can assume that a and bm is not 0. Then if you look at f of x times g of x, this is with first term is a0, b0. There is second term, etc. But the last term is an times bm times x to the n plus m. And an times bm is not 0. So that means f of x times g of x is not 0. So that if you take any two elements from the ring Rx, then their product, two non-zero elements, then their product is not 0. So that means, therefore, Rx has no zero divisors. Has no zero divisors. So that it is an integral domain. Okay. So for example, so Z is an integral domain. So that Zx is integral domain. So if you take in a field, so if R is a field, let's say F field, if F is a field, then it's an integral domain, so that f of x is an integral domain. So these are the polynomials over field are the most important polynomial rings. Okay, next we have, if you look at this example, for example, Z6, for example, Z6 is not an integral domain. It's not integral domain. It's a commutative ring with 1, but it's not an integral domain. The reason is 2 is not 0, 3 is not 0, but 2 times 3 is 0 in Z6. And if you look at the polynomial, f of x is to be g of x, f of x to be 2x, g of x to be, let's say, 3x squared, so that f of x times g of x is 6 times x cubed, which is 0 times x cubed, which is 0 polynomial. So that, but this f of x is not 0, g of x is not 0, not 0. So that, so therefore, we found 0 divisors in Z6x as 0 divisors. As 0 divisors. Oops. Time's up. Z6 has 0 divisors. So that is not an integral domain. So this is the end of this lecture. I will continue later.